Okay, so we're going to dig deeper into this data with the free reduced lunch and the passing math. So remember, the calculator calculates the least squares regression line. And then we're going to use that regression line. It says the nearby Amber High School has 40% of their students on free reduced lunch. What does the least squares model, predict past the math test? So 40% on free reduced lunch, that's your X, right? That's your free reduced lunch. That's your explanatory variable. So you're going to put 40 in for X. Now you don't have to make it 0.40 because the table already has these as percentages with whole numbers. So you want to match whatever your data table has. So in this case, whole numbers, so we're going to use 40. And when you do that, you're going to get 57.788%, right? Just grab a calculator and type it in. All right, Amber High School, is that outside of the scope of the model? And the answer is no, right? 40 is right in the middle of our data, right? So that's not outside the scope of the model at all. Now, if X was 80, that would be outside the scope of the model, would be. All right. Now, let's see. Determine the residual. Oh, okay, so we'll have to get out the formula for residual. Residual is the error. Oops. That's equal to observed minus predicted. Okay, so that we observed in real life 51. We thought it would be 57.788. That leaves us to a residual of, let's see, negative 6.788. If I'm doing the math correctly in my head, which I think I am. And there we go. There's our residual. All right, so interpret that residual. Well, it appears that Amber High School is not doing well. Almost 7% lower passing rate than we would expect. So sorry, Amber High School, you're not doing so good. Luckily, you're made up, so there's no students actually suffering. No students were harmed in the making of this example. Let's put it that way. All right, done with that. All right, so now what about the slope and the y-intercept? So when you look at the equation y equals ax plus b, a is your slope, okay? So in algebra class, they teach it to you as m. In this class, we'll treat it as a. And then the y-intercept is 0, comma b. Technically, it's a point, so you need to have an x and a y, and the x is 0 if you're on the y-axis. So that's 0, comma b. That's your y-intercept. Now, how do you interpret them? So the interpretation for slope is for every increase in x, quote unquote, by 1, the y, quote unquote, goes up or down by a. And I'm putting the quotes in there because you have to state it in English, right? State in English, not with the variables. I'll make a note. Technically, it's for both of them, so I'm actually going to throw this note down here at the bottom because it's true of both of these things. You need to state your results, your explanations, in English, not with variables. Boom. All right. So let's think about our slope. Our slope for the lovely high school data was negative 5.0. Oh no, it's negative 0.28. Sorry, my bad. 0.28. Okay, so that's the slope. Now, what does it mean? Okay, so we have to write it out. For every increase in x by 1. And the 1 is because it's a over 1. It's technically negative 0.28, if you want to see it. It's technically negative 0.28 over 1. Anything is over 1, right? And then it's change in y over change in x. So this is the y as x changes by 1. Right? So it's the same interpretation that you would use in an algebra class, if you will. And that's not entirely correct to use that for statistics, but that's what we're going to use. All right, so for every increase in now we got to explain what x is. The percent of students on free reduced lunch in a school by 1%. The percent, now the Y, the percent of students passing the state math test goes down, because this is a negative, so it goes down by 0.28%. Okay, so every time the percent of students on free reduced lunch goes up by 1%, or by 1, honestly, because you said the word percent, the percent of students passing the math test goes down by 0.28. Right? So I'm explaining in English what X was, that's percent of students on free reduced lunch, and then what Y is, that's percent of students passing the math test. I'm stating those combinations in English. French won't do. All right, so then what about the Y-intercept? Okay, so the Y-intercept is 0, B, and B was 69.1. Okay, it's a point, so you have to give it coordinates. Okay, so let's see, a school that has 0 students on free reduced lunch should expect a passing rate of 69.1% on the state math exam. Right? So when you have no students on free reduced lunch at all, you should expect about 69.1% to pass, which is quite low. That's because it's quite hard to get everybody to pass a test like that. Now, is that Y-intercept outside the scope of the model? All right, so let's remind ourselves what our data is. Our data, the lowest data point we have is down here at 15%, which would be quite a wealthy school, right? 15% of the students are on free reduced lunch. Okay, so 0, which is where this is, 0 students on free reduced lunch is far away from our data, right? X equals 0% on free reduced lunch is far away from the actual data we had. Oops, sorry, my computer's being possessed. There we go. Okay, so because our lowest value was at X equals 15% or so. Right? All right, now suppose a local private high school wants to use the least squares regression model to make predictions as well. Why would that not be appropriate? Well, the key right there is the word private. Because if you recall, this data came from public, see right there? Public schools. Okay, so that would not be appropriate. You don't want to compare apples to oranges. So all the data were from public schools. So there's no comma in there. So they should, I guess there is. They cannot be appropriately applied to a private school. Private school has different rules, different everything, so it wouldn't be fair. You don't have any private schools in your data set. Now, if you had private and public in your data set, you'd be totally fine, but you don't have that. All right, last but not least, I wanted to show you this kind of cute little graph here. Well, actually, I'm going to make a graph to go with it for this comic, which is, why is that woman scowling at me? Do I know her? She's really grimacing at him. And she says, if she loves you more and more each day by linear regression, she hated you before you met. Now, I made a little graph to kind of show what this means. So let me shrink this down so I've got room for my graph to fit in here. And I did this by hand. So insert, let's see, the picture, the love-hate picture. There you go. All right, so I've got love on a scale, right? So love is on the top side, hate is on the bottom. And then, you know, you love them more and more every day. So some days you love them a lot more, some days a little bit more. You know, they make you happy the first day, sad the second day, right? But you love them more and more every day. And then here are the days that you know them. Oops, sorry, my computer's being possessed. So you love them more and more every day. Then here's where you met, right? Technically, you didn't love them. You just met them that instant. And then down here, by linear regression, that line goes negative. It's kind of making a joke about how outside the scope of the model, right? If you go back in time far enough, you make something crazy. And that's what this is talking about, right? It's making a joke about, if you go too far back in the past or too far in the future, it doesn't make any sense anymore. And that's what's going on there. All right, we're all done with 4.2. I'll see you back here for 4.3.